Let's get fired up. Go for a little bit. That. All right, so today we're going to try and finish chapter 5. We've got a bunch of stuff to talk about today. In particular, maybe I'll write this just over here a little bit. I'm going to try and talk about Newton's third law today. I'm going to try and talk about systems, and internal / external forces. And then finally, maybe we'll do some strange constrained motion force problems. Those are pretty interesting. If you're curious what I mean by this, a simple example might be like the block and tackle. And if you don't know what that is, we'll look at it later today. All right. So I'm going to try and leave that up there to remind myself of what we're going to do. And then it's just for me. All right. Let's talk about Newton's third law. And this is on page 88. The common way of saying Newton's third law is action, reaction. All right. In physics, we'll probably say it like this: force vector of object 1 on object 2 is equal and opposite to the force that 2 exerts on 1 vector. Okay. Now, I would typically call this the action, and this would be the reaction. So when we say action, reaction, we're talking about forces, literally. So there's an action force and then a reaction force. And I want to point out something right away. I want to point out this crucial fact. One of these forces in an action-reaction pair is acting on object 2. The other one is acting on object 1. Now, why am I belaboring this point? It's crucial that we notice they are not on the same object. That's a fundamental thing that you should just now accept for the rest of your life. They're never on the same object. Action reactions are always on different objects. Okay, that's crucial. I think a sentence can help. Let's say we have an action. And let's say the action is the earth pulls down on a box with gravitational force. Okay? And for me, when I write the sentence for the action, it helps me understand what the force is. In particular, notice it talks about, here's one object. What is the other object? It's the box, and that's kind of sloppy, so let me write that a little bit better. There's two objects. Okay. Notice there's a direction. And there's a type of force. Okay, when I write the reaction, for me, the easiest way is to just play with the sentence and work it around, and that always gets it right. In particular, let's compare that sentence to right here. what happens to the objects? They flip. So instead of starting the sentence with earth, I must start it with box. What happens to the direction? So it's now, instead of pulling down, it will be pulls up on what object?
Earth.
On the earth. With what type of force? Same type of force. Now, I wouldn't be spending this much time on it if it wasn't going to be crucial for us getting the rest of the lecture right and working on this in the next chapter, chapter 6, where we do friction. So, yeah. Just no, yeah. All right. Any questions about this? It might feel a little uncomfortable. People don't think about boxes as pulling the earth upwards. Now, keep in mind, right now, I am pulling the earth upwards, right? When I jump up in the air, I'm pulling the earth up to meet me. However, what do we know about the earth's mass? Is it big or small? Huge. So the issue is, just because you're exerting a force doesn't mean the acceleration is noticeable. You see what I'm saying? So you know, for example, force equals ma, right? So if we think about, for example, this case, you could say the mass of Rob times the acceleration of Rob, right, might be equal to the mass of the earth, and the acceleration of the earth might be really tiny, right? And this is in fact what's happening when I jump up in the air, right? You notice my acceleration because my mass is very low. We don't notice the earth's acceleration because its mass is very huge. So that's why people have trouble with this, all right? But in short, this is the key takeaway. If you are asked on test 2, not test 1, this is chapter 5. Remember, test 1 is only on chapters 1 through 4. Remember to start practicing with your scientific calculator because you're not grabbing calculators on the test day next week. The test is Monday. You know all this. Okay, look. On test 2, I'm going to ask you a question like this. Write down a sentence and then flip the sentence and you'll get it right every time. If you don't write the sentence, you'll screw it up. Good enough? Now, let's do some examples. I need 2 students, one with large mass and one with negligible mass. Well, that's going to be hard. Or just a student that weighs a lot less than me. I need somebody to come over here. Still on Zoom? Yeah. Want to just come over? You're right here. All right, we've got these 2 hovercraft. Now, let's talk about this. So notice there's a power switch on the blower. You see where that is? That's how we can fire that up. Okay, so we're going to sit on this, and what we're going to do, we're going to hold this between us. Now, just practice up top. Is it still visible on Zoom? All right. So the idea is we're going to push without holding it, like shove, like push, fly away, and we're going to push like this. All right. So let's go ahead and do this on the count of 3 here. Yeah, and I would sit cross-legged. Now I just did lunges yesterday, so I've got delayed onset muscle soreness. I'm like, oh my gosh, my legs hurt. So yeah, we're gonna turn this on. You can move around if you want to see better, all right? And just remember, just kind of keep an eye on where the zoom screen is, right? You're good. Okay. Now when we do this, how much do you weigh? Oh, geez. Oh, God, that's embarrassing. My mass is twice yours. I'm about 250. So I have about twice the weight here, or twice the mass that he does. So when we push here, right, who's going to be pushing harder? The same by Newton's third law, right? I push on him the same that he pushes on me. Now there's a question you might have about this. But this is very light, right? This weighs almost nothing. So I want you to imagine this has negligible mass. It's basically a way to extend our arms. So when we push, I can't push harder on him than he pushes back on me by Newton's third law. So we should have the same force exerted on each other. Who should move more? Yeah, he's going to move a lot more than me, about twice as much. And then it turns out I'm so big, this hovercraft gets so much friction. What's up, Megan? Ready? So let's do it, and then I'll do 1, 2, 3, push. All right, go ahead, come on back here. I want to do this experiment again. Can you bring that hovercraft back? You can turn it on and just come back to it. Yeah, it's easier to turn it on and then show it. Or, oh yeah, you do it. All right, and then keep a little bit more this way. Alan, see in the middle of the Zoom screen? Yeah. All right, go ahead, do it again. This time what you're going to do is he's going to throw this medicine ball. In this case, who's got more mass? Him or the medicine ball? So then when he throws the medicine ball, which will accelerate forward? Medicine ball or hit? Exactly, same force, but lower mass. Okay, so go ahead and sit down. Okay, turn it on and then throw it at me as hard as you can. Get centered a little bit more. There you go. Try it now. Oh, you have to have it first. Then go ahead and turn it on. You barely moved at all, right? Let's give her a round of applause. So the idea there I feel like we could do some sample problems on this. Let's look at problem 5.20.5 on page 90. I'm deliberately going to leave a little bit of information out here. And actually, I want to draw this box a little bit bigger. Easier for me to weigh. Okay. We're going to start with this situation. I'm going to kind of neglect whether we have friction or not in this experiment, but the main idea, I'll explain the main idea at the end and make sure you get the main idea. And then we can discuss friction in the next chapter. So in any event, we're told we have these two blocks. And then in this case, the mass 1 is equal to 1.00 kilograms. Mass 2 is 2.00 kilograms. And the blocks are going to be pushed by some sort of zombie over here, like this. There's some sort of zombie pushing on them. All right, good enough. All right. I could even call that force subscript Z for the zombie. Now, block 1 will exert a normal force on block 2. Do you agree there's a surface right here? So my claim is there will be a normal force from 1 on 2. Whoops. I read the word on. Sometimes I get really lazy and just call this N12. Okay, I leave out the word on. There's a force the other direction on 1. There's a normal force of 2 on 1, or sometimes I'll just call that N21. In the first problem, part A says acceleration equals 0. Right? Do you agree it says if the blocks move to the right at constant speed, isn't that the same thing as telling you the acceleration is 0? So in this case, if the acceleration is 0, which one of these forces is bigger, N12 or N21? Does one push on two harder than two pushes on one? Remember, two's got more mass. Which one has more force? Same. I'm trying to trick you, right? I'm trying to trick you, but you didn't fall for it. Good job. You agree that N21 is equal to N12. However, what if A sub x is greater than 0? It's accelerating to the right. If it's accelerating to the right, which one of these forces is bigger? Same. I'm just trying to mess with you. They're the same whether you're accelerating or not. Okay, so that was the point of this, all right? I'm trying to set you, I just want you to believe this, and we saw this, it works, nothing crazy there. However, okay, and this is all based off Newton's third law, N3L. Everybody okay with that? That's just straight up Newton's third law. You have two blocks of direct contact. Let's now look at 520 3/4. I know it's silly. I know. I didn't want to have to renumber, and I didn't put in an auto numbering feature when I first did it. So moral of the story is take the time to put in an auto numbering feature. I didn't want to have to renumber all those solutions either. Yeah, I'm just like, oh, and I wanted old versions of the book to work. So whenever you see a fractional problem, it's up on the website if you don't have it in your book. All right. Got object 1, object 3, Gesundheit, object 2. In this case, mass 1 equals 1 kilogram. Mass 3 is 3 kilograms. Mass 2 is 2 kilograms. So we've got the heavy one in the middle now. Right, the biggest one in the middle. And obviously these aren't just floating. They're sitting somewhere on a surface. It's supposed to be horizontal level. We're going to ignore worrying about friction for right now. Okay. In this problem, we're talking about different normal forces. Let's read carefully. Oh, and there's a zombie pushing, right? There's still a zombie pushing. Still the old zombie pushing these blocks around. All right. Now in this case, it says block 1 exerts a normal force on block 3. There's a normal force of 1 on 3. Block 2 exerts a normal force on 3 as well. Which way does block 2 exert a normal force? Okay. Okay, so we've got these two normal forces. Part A is again, what if the acceleration is 0? Which one of these forces is bigger if the acceleration is 0? Why do you say that?
Because 3 is going pushing against 2. Oh no, sorry. Wait. Although, wait.
Yeah, we can ignore friction for right now.
Force is bigger.
Okay, so you can pretend there's no friction in the universe, all right?
Oh, the 3 on 2 because of the mass is bigger.
No.
Oh no, it's an equal. Wait, it is an equal
Because of what?
Because 3 is pushing on 2, and then that causes 2 to push on 3.
But you were saying something about action reaction, right?
Oh yeah, every action has it.
That's not valid.
Oh,
Action reaction applies here where it's the same two objects. And that's what I wanted to check. I'm trying to trick you again, but in a different way. Now look, here, these are an action reaction pair because it's 2 on 1, 1 on 2. This is not an action reaction pair because this is 1 on 3 and 2 on 3. Notice how they're both on 3. So this is not an action-reaction pair problem. Do you know any other? So it's not a Newton's third law. Do we know any other Newton's laws? What's the one
Force
equation?
equals mass times acceleration.
Sum of forces in the x equals mass times acceleration in the x. Now, in this case, I know I said friction 0. Just give me a minute. Right? Pretend the zombie force is 0, right? If friction is 0, this problem doesn't make a lot of sense, but I really wanted to just focus on what I just talked about with him. But let's just pretend right now that somehow this thing is going to the right with constant speed. I'll explain more in a minute. What does that say about these two force vectors? That would be positive. This would be negative. And what would it equal if there's no acceleration? 0. So what must be true about the size of these two? They're the same. Now keep in mind, if you're pushing this thing to the right and there's no friction, this thing would actually accelerate. So the only way this problem would make sense for part A is if the zombie force was 0, and then both of these would also happen to be 0, but it's still true that they are equal. Weird. Now let's say what happens if it's accelerating. If it's accelerating, and again, we'll ignore friction here. If it's accelerating, which one's bigger? Or are they the same? If this block accelerates that way, which arrow's got to be bigger? The blue one or the green one? The blue one. Don't overthink it. It's the same equation. Do you agree? You have it. Look at the equation. Now look, do you agree this would be a positive quantity? We said A is positive, so that means the positive number has to be bigger. Otherwise, you don't get a positive quantity on the other side. My goal here is to point out this uses Newton's second law. This is using Newton's third law. Here is the point of all this, and right now we could, in the real world, there's going to be friction, and that would make this more complicated. But this is what I wanted to emphasize with these problems. Number one, remember that Newton's law applies when you have two blocks in direct contact, and we're talking about 1 on 2 or 2 on 1. Over here, when we're talking about this problem, we're talking about the forces on a single block. We use Newton's second law. Understood? I have a question for you. When we were doing the hovercraft demonstration a minute ago, did the hovercraft demonstration look more like this problem where there were 2 blocks or this problem where there were 3 blocks? Just go with your gut.
Two blocks.
Okay. I would say 3, because I'm thinking the cardboard tube was the 3rd block between us. Now, what's funny though is the math is actually closer to the 2 block, and let me show you why. Remember that cardboard tube was really, really light?
Negligible.
And so if the mass is negligible, if you have a negligible mass, and keep in mind, this would be mass 3 here. If this was approximately 0, then we get right back to a Newton's second law type problem. This is why we do tug of war problems or these problems where people are pushing on each other. If there's something between them that has negligible mass, it's approximately a Newton's third law problem. So the math definitely looks most like this with the cardboard tube, but strictly speaking, it was actually this problem. So far, so good? All right. All right. Let's try another one. Let me go 4. Come on. Go this way. Oops, wrong way. Okay, and then we're right Yeah, could you scoot over a seat or two this way? Yeah, just jump over a seat. And who else do I got there? I think I'm getting the back of your head. Yeah, yep, you. Yeah, sorry about that. All right. I appreciate you guys always being willing to move. By the way, those of you out there on Zoom, let's give a round of applause to the class. Class, give a round of applause to yourself for dealing with it. There you go. Here we go. I'm looking at questions in the book. If you're curious what I'm about to do, I'm looking at questions 421, 2, and 3, or what's 5.21, 22, and 23 on page 90, just below the ones we just did. You see the ones with the fan cart? And actually, you want to just come up and help me out? And just stand. All you gotta do is catch. I'm not gonna. Nothing's going to fall apart. I don't think. All you gotta do is catch this. Yeah, and catch this, and don't get your fingers in there. Right?
Oh, okay.
Got it?
Hopefully it's not too fast.
Yeah, it's not too bad. All right. And so the idea here is, I don't know if you can see this, but there's a little arrow that says the wind direction on this fan. If you guys need to move so you can see, come over here, just kind of watch out for this panel. So if you guys want to stand up and walk around so you can see, that's cool. And then if you're able to, stand that way they can see a little better. All right. Yeah, perfect. All right. And then just kind of catch a little bit in hands like that. That way it doesn't like those things. All right. So nothing fancy here. There's an airflow indicating this way. The fan is going to push on the air that way. Which way is the car going to go? The other way. What is the force that makes the car go that way? Friction. What object, so to speak, is pushing on the cart? Air. The air, the fan pushes the air this way. By Newton's third law, the air pushes on the fan that way, right? Nothing crazy. Got it? And then you can turn it to the middle to turn it off on this end. Yep. All right. So now we're going to try it again. Now what I'm going to do, I'm going to put this sail on here. I'm going to push the air the same way, but now there's a sail. Hopefully it's pretty well aligned. It's never perfect. My question is, when I put this sail on here, this big flat piece of metal, what should happen when I turn the car on? Discuss with your neighbor. If you want, you can walk over there and talk. I'm going to get it drawn.
Is it set up you think the cell is going to push at the air now, or the air is going to push with the cell?
I'm trying to just gonna stay still. It's gonna do anything.
Do you think it's going to sit still?
What do you guys think?
Think it's going to sit?
Possibilities either it might stay still or it'll go backwards. No, I doubt it would be going backwards.
I think it might go backwards, but not as far.
Actually,
Panel, maybe.
yeah, that's what I was thinking because of the air. Like you said.
Either go down or down faster, or it'll just stay still. I think it's more likely. Yes.
Sorry.
But maybe it will bounce off the panel. Then.
But
I
you
don't know
can,
how that works.
yeah, I'm trying to compare this to a boat that doesn't have the head on the same.
Yeah.
So that's really unlikely. And
Yeah. I would say.
All right. So let's take a look on the whiteboard here, and then we'll come back to the demo. Give me a second. Okay, so 521 was like this. I think that was 521. We said the fan pushes the air this way, so the air pushes. Do you agree that force is still going to be there? So assuming I line it up the same way. Fan pushes air this way, so there's gonna be a force this way. Now, what's gonna happen? The air is gonna be flying this way, right? When we do that, what direction will the sail push on the air?
Right.
So the sail this way, right? By Newton's third law, which way does the air push on the sail? The same way or the opposite way, right? In theory, if the sail is strong enough to completely stop the airflow, what should be true about this object? It should stay at rest, right? If these two forces balance. Now, what if a small amount of air is able to leak out around the edges? Then maybe the forces won't balance. Let's take a look at it and see. Give me a sec. Here it is. Okay. You ready to catch this one? Well, this one, hopefully you don't have to catch, right?
Yeah.
And so this, here, you can hold this for a second so it's out of the frame. All right. Watch out, it's really goofy. Okay, so now, again, isn't that weird? Okay, this is what we expect. If I take the sail off, whoa, what'd you? All right, now here, jump. All right, so that's working pretty well. And to be clear, what I was saying just a second ago is what if we only like cover most of the air, right? Then, well, in this case, it's still blocking most, maybe the batteries are starting to die, right? Oh, whoops. All right, so now come to the fun one, right? In this case, we're still going to point this thing the same direction. The airflow is still this way. We'll put this on here. My question is, what's going to happen when I turn the air on? In this one, go ahead and discuss. I'm going to draw the picture real quick.
Absolutely.
Because I'm pretty sure some of the air would escape.
It'll take a little while for.
Some of it, but I think the most of it is all the way through.
Probably
True.
this
Because
way.
they have to push. Well, oh wait, but when it hits the back of the wall, then they'll be pushing this way.
We're gonna go to the right.
So that would cause the normal force to go. Wait,
Must stay still for a little bit.
yeah, the wind would push this way.
Probably gotta stay
the
still
back
for
of
a
the
little
wall,
bit. Then look to the right.
I don't know.
Force those trying to trick us.
Maybe I should go back.
Am I? Okay, so let's think about this, right?
Oh,
Do you agree the fan is still going to push the air, and this time it's going to push it into that tube? So by Newton's third law, the air will push that way on the fan, right? Fan pushes air this way, so that's still the same in every single version. Now, what's going to happen to the airflow in here? What do you think is going to happen with the air? Which, well, do you agree it's going to come out the other end of the tube?
Yeah.
It's a big hollow ducting, right? That's how ducting works. Which way does the tube push on the air? Look at the way the air's motion has changed. The air was moving this way. Now the air is moving that way. Which way did the tube push on it? So now my question is, which force is going to be bigger? Or are they the same? What do you think? What's your gut tell you? You say the same. Why?
Still the same force?
Well, let me ask you this. Think about the fan. The fan takes the air from 0 miles per hour to 5 miles per hour that way. What does the tube do? The tube takes it from 5 miles an hour this way to approximately 5 miles an hour that way. Which thing, right? Look at it. The velocity has changed directions. Now I'm just making up these numbers, right? 5 meters per second, 5 miles per hour, whatever, right? The wind speed going this way is then reversed by the ducting. So in this case, the fan only has to get the air up to speed, whereas the ducting not only has to stop it, but then reverse its direction effectively. Which one do you think has to push harder? The tube. Probably about twice as hard. It takes more energy to reverse, or more force to reverse the direction of something than it does to stop it or to start it. Because, okay, so now based on this, in this case, which way does the air push on the tube? Right? Think about it. The tube's saying, air, go that way, air, go that way. So the air's like, tube, go that way, dude. It's a weird demo, isn't it? Let's take a look. Isn't that kind of fun? I don't know. I hope it's kind of fun. There it is. So in this case, which way is it supposed to go? I've already forgotten. Okay, so when I turn this on, here we go. Does that make sense? Oh. What do you think? Any sense at all? Yeah. Oh, geez. Let's give him a round of applause. I think that's kind of interesting. All right. The school wrote me a nasty email because I bought that piece of ducting. They're like, you're not doing anything with that. You should. Oh man, I don't want to go into that. But that's what I think of every time. I got a nasty email trying to build a demo for my students. Oh, the joys of doing physics. Nobody understands. Nobody understands me. All right, whatever. So far, so good. Okay, that's Newton's third law. Know it inside and out. Write a sentence, and that helps you flip it. If you need to get the action reaction, is it coming on a test? Yes. Is it coming on your final? Probably as well. So just know that you've got to do that. If you need extra questions to practice that, where are they? I think it was page 89. 89 also has some. So basically 88, 89, and 90. That's all your Newton's third laws. Got it? All right. Next up is going to be systems on page 91. And I'm going to erase the board and get ready for it. So we're doing systems, page 91, or just above question 5.25. If you got an old version. I'm going to erase the board. You can talk amongst yourselves if you want, or whatever you need to do while I'm erasing. You can read that paragraph.
91.
Yeah, page 91, just before question 5.25.
5.25.
Board is getting harder and harder to erase. I think there was some chemical or something sprayed on it. Close enough. Systems. And we're going to start with question 5.26. Now I know a lot of you can probably do this problem already. I like this problem for talking about systems, internal versus external forces. Okay, so in this case, we're going a little bit deeper into this zombie pushing on these two blocks. Got two blocks, horizontal floor. There's an applied force with magnitude F. Friction is negligible. Does anybody have an idea how you could make friction negligible based off the demos we've been doing today? Oh, true. You could use like an air hockey table. Absolutely. What's another way?
Space.
Put little, well, that's true. I was going to say put little wheels on the bottom of something. Like a suitcase has wheels on the bottom, makes it less difficult to drag it. I don't know if you noticed we were dealing with these carts all day and they all have little tiny wheels on the bottom that are very low mass. So you might be saying, well, what about the energy used up by the wheels? Well, if the wheels are really light, if you put really light, tiny little wheels on there, you can basically reduce friction to a negligible state. So it is realistic in certain cases to ignore friction. Again, just imagine if these blocks had tiny little wheels on the bottom, right? It would be fine. So far, so good with that. Now, I want to ask you this. If you push on something and there really is no friction, what's going to happen to these blocks if you push on it and there's no friction?
Slide.
Which way?
The way you push.
Yeah. Are they going to accelerate or do you think they'd be at constant speed?
Depends if you push with the front speed.
Well, let me ask you, if there's no friction, is there anything to oppose this force?
Maybe air resistance.
Okay, we're ignoring air resistance too. Negligible air resistance, negligible friction. So if there's no air resistance, no friction, is there anything to fight back?
No.
So then it's going to accelerate. If you're not sure, we can always just assume it's going to accelerate. But in this case, the problem even tells you that. Basically, this is what I wanted you to know. If you have an unbalanced force, the objects will accelerate, right? And if there's no possible force to balance this one, they must accelerate. And that's the fact that I was glossing over in those earlier demos that we were doing with the blocks 1 and 2 and 1, 2, and 3 with the Newton's third law. So now we know without friction, it would have been impossible for them to move with constant speed, right? It would always have to accelerate. All right. In this case, let's do an FBD for M1 and an FBD for M2. All right. In particular, somebody tell me one force that's acting on object 1. Give me one force.
Force.
Okay, capital F. I like it. Anything else? Normal force. Which way? Okay. What surface is causing the normal force upwards? The floor. Now, I want you to succeed, so I'm going to tell you just, there's lots of different ways to label these. I'm going to label this one N. I could label it N1 floor because normally your normal forces have to be between two objects. However, in my solutions, I usually shorten that to just N1. The normal force upwards on 1 from the floor. So if you see a normal force in my solution, that's just got a single subscript, that means on 1 from the floor or from the incline or from whatever. Anything else? I'll wait for it. MG, you guys are awesome. MG. This is not good enough. Why? Yeah, when we get 2 blocks, it's critical that we start keeping track of everything. So subscripts matter. Anything else? Yeah, there's a normal force to the left caused by what? 2 on 1. Now I'm going to say N21. Okay. I'm singling this one out for reasons that will become obvious in a second. Let's look at the free body diagram for number 2. What is one force that acts on number 2? Anything. What's that? N1 was the normal force from the floor on 1. Did you mean N12? Meaning, oh, okay, yeah, it's mass 2, so that might not be the same normal force. So we're going to call that N2.
Okay, I see.
Does that make sense?
Yeah.
Yeah. And the main reason for doing this problem is getting you used to my notation so that you can read the solutions effectively. Good. Does that make sense now why I'm calling it N2?
Because they were different MG.
Exactly. They might not have the same mass, so we can't expect them to have the same normal force from the floor. Well, you just said it, mg, right? That's going to be in here, right? That's m2g, because it might not be the same. And now we see these subscripts get critical. What about capital F? Is the zombie pushing on block 2? Yes or no? No. If force is acting on 1, I don't draw it on 2. It's just not there. Huh? Why does block 2 get pushed that way? What pushes on block 2? Yeah. Now, who pushes harder? 1 on 2 or 2 on 1? Or does it depend on the mass? Same, by Newton's third law. Now you know why I did that first. Do you agree these are the same? So I want to point out, I could also write N21 here, or I could write N12 here. Do you agree it's the same magnitude? The direction is flipped. So remember this, on a free body diagram, the force is magnitude and direction. It's okay that they have the same magnitude and they have opposite directions as indicated by the arrows. Cool with that? What is the force that pushes to the left on block 2? What force pushes left on 2?
I'm gonna say F, but I'm not sure.
No. If there was, okay. If there was friction, it would be, but there's not friction. So if there's no friction, what force pushes to the left?
Nothing.
Nothing. There is no force to the left. And I was just checking, right? Just trying to trick you and seeing if you can hold up when I'm trying to trick you. There doesn't have to be a force to the left every time. There doesn't have to be a force up. Sometimes there's just, that's what it is. And that's it. Are you okay with that? Apologies if I'm just trying to make sure that on test day, you don't get freaked out if you see an example like this where there's no force to the left. Sometimes that happens. And to be clear, this is on test 2, not test 1. All right, give me a force equation for this. How about the x direction? In the x direction, give me a force equation. There's your coordinate system. F minus
2-1.
N12, N21, doesn't matter, right? Anything else left or right? So what does that equal? It doesn't equal MA, it equals
0.
M1A. You know what I'm saying? I'm just trying to be super picky because over time, if you forget a subscript, that can really waste your time. All right. How about the x direction for this one? N12, N21, we could use either one. Equals M2. Good with that? Everybody feeling good? We know that A is positive in the X. That's why it's positive in it. All right, now I want to do something new. I want to draw an FBD of the system and learn what it's good for and times we might want to use it. So this is all kind of standard, whatever. I'm going to draw this approximately real size here. Whatever. So we have these two blocks. What is one force that acts on this 1-2 block system? It's like a mega block, right? What's one force that acts on it? I heard a normal force. Is it going to be N12, N1, N2, or something else? This is the special one that I just call N in my solutions. When I'm doing a system FBD, I'm like, you know what? This is just the normal force on the entire system with no subscript. So I know this is tough because there's lots of different subscripts, but summarizing, 1-2 or 2-1, that's between blocks 1 and 2. Subscript 1, that's from the floor on 1. And 2 would be floor on 2. And here, no subscript, floor on system. Okay, and I apologize that it's complicated, but that's my system in the solutions, and I hope that helps you understand the way I write the solutions. Any questions about that? What's another force on there, on the system? Gravity. Is it M1G? M2G? Mg, okay, what's M? So let's just write that, M1 plus M2 times G. Do you agree it's the net? Okay, okay. And like you said, you could call it M total G or Mg, where M equals, right? All that, that's all good. Anything else pushing on the system? Force F? Okay. Anything else? In particular, what about the normal force between the blocks? Does that exist?
It's one system.
It exists, but do you agree it's pushing both ways at the same time inside the system?
Yeah.
Oops, I think I switched them, but. And we know it doesn't really matter if you switch them. So do you notice this force is called internal? And what happens to the internal force? It cancels out. So this is an internal force. This is an internal force. Everybody okay with that?
Yeah.
Now, in this case, notice internal forces not needed in system FBD. That's what I was trying to get out of this. Everybody cool with that? All right. What are the other forces called? External. So notice these are the external forces. N, F, and W, the weight, are external forces. And to be clear, right, N is a vector if you include the magnitude and the direction. Capital F is the force magnitude and the direction. And the weight is mg and the direction. All right, so far so good? Can you not read, or did it make sense, or?
Oh, yeah.
Okay, just making sure, yeah, if you can't see something, just let me know. Sorry about that. All right. So let me ask you this. What's the force equation in the X for this one? F equals what? Which M? M total, M1, 2, whatever. Notice it's crucial that when you're doing F equals MA, you use the mass of the object in your FBD. In this case, the total mass. Okay, if you know the force and you wanted to get the acceleration, which is the obvious FBD to draw? Which is the best way to get the acceleration really fast? The system. Do you agree it's going to get you right there, right away? Or do you agree if you know the acceleration and you want to get the force? Sometimes you're like, man, I wish I could make this funny car accelerate at this rate. I need this much force. Okay, it's fine. But, oh, go ahead.
Does the A have to be A subscript X or just? A?
Well, in this case, do you agree A sub Y equals 0 and A sub X equals A because of this picture?
Okay, yeah.
Yep, good question. Excellent, excellent. So I kind of cheated here, right? Yes, this should be an A sub X, and then I just immediately plug in that A sub X was A. Good clarification. Okay, going back to these. We see that the system FBD is awesome. So why would we ever do these other ones? What piece of information can you get from these other FBDs that you can't get from that one? The internal forces. So if you need to learn about internal forces, a system FBD is useless. Is there ever a time you might want to know about the internal forces? What's that?
Pressure, maybe?
Yeah, something like that. Imagine you're working for Amazon and you have these boxes and you want to make sure the boxes don't get crushed. Maybe you know a certain amount of force that the boxes can withstand. So maybe when you put them on this conveyor belt, you want to make sure your conveyor belt has the right speed or angle or acceleration such that the internal force between them is always below the crush strength. So, okay, or something like that, right? There's times where you might need to know, or maybe instead of having a normal force between you, maybe you have a cable. And maybe your cable can withstand a certain rating before it snaps. And you'd be like, man, I got to make sure I know the tension is less than the snapping, the maximum tension that the cable can withstand. So far, so good? All right. I'm going to say this. There's some other good questions on that page, like 525 and 527. 525 looks really scary. But keep in mind, you're not actually doing the FBDs. All I'm asking about is what forces are internal on that problem. So if you just want to practice which forces are internal, you could try problem 5.25. If you want to do another problem, I think the one at the bottom, I think, was actually an old test question or something, right? So that you could look at 5.27 at home as well. All right. Okay. How are you feeling? It's been almost an hour. I like to make the last half of class shorter than the first half, but are you okay? That means I got to start another problem, which is probably going to take us 20 minutes. You guys got 20 minutes and then a break? Okay, let's do it. It's nice to end with a fast half. Okay, so take a look now. Let's see if we can put some of this together with 5.28 at the top of page 92. 5.28, and I'm going to take a look at it over here. Yeah, it looks crazy. It's only parts A through L, but we're only going to do some of it. All right. You like how I tell you that before you go? Before we go for the break, let's do parts A through L. Oh my gosh. If you need to take a quick break, you can do that at any time as well, by the way. So yeah. If you're really hurting, take that break. All right, here's the deal. This is called an Atwood machine. You can see I've got these two scales here. Is that showing up?
Yeah.
All right, thanks. And the idea here is I just put some different masses on here. So in this case, right here, I have a 500 gram mass. How many kilograms is that, approximately? 0.5, what's G, approximately? 10, so how many newtons is this? 0.5 times 10 is 5. Let's confirm. It's about right. You know how crappy these scales are. Okay. Now I have 550. So this is just a little bit more mass. Ooh, I want to switch these actually. Oops. Well, I know what to do. I'll put this one on here. Just show you that it's the same. Right, do you agree that's 5? Now when I have the same mass on here, the acceleration should be balanced, right? If I put a little extra mass on here, even that tiny amount of mass is enough to get this to accelerate. Because these pulleys, the bearings are pretty low friction. There's a little bit of friction, but in practice, the friction is negligible. So I'm going to release this from rest, and you can watch it. And we see it accelerate. Do you agree? That's the problem that we're trying to analyze. And I want to teach you about the basic concepts that we're going to use on this over and over again. And in theory, even though these masses, now I don't know if you noticed this. This might not be enough to be visible here, but when I let go of it, let's see if the tension changes a little bit. Did you see it? Watch the tension change just slightly. Almost negligible. Now it's probably because these mass, if I put a little bit more mass on this. Now, what do you think is going to happen if I use more mass? What should happen to the acceleration? Don't overthink it. Should go up dramatically, right? So now I'm going to hold this on here. Oops. I'm going to get this one to hook on there. Get this right. All right. What would you think if I was your math teacher next semester? Would that scare the crap out of you? I'm thinking about moving over to math. It's a lot easier to teach math. Right? Okay, now here, this scale is totally janky. There, looks perfect, right? Now, when I drop this thing, I want you to think for a second. When this is accelerating down, do you think the scale should still read 10? What direction is this mass going to accelerate? Downwards. So which force is bigger, the weight or the tension? So the weight should be bigger than the tension. Right now, the tension reads 10. Did you see it drop? I'm going to do that one more time. I can only do this so, right, there's a short. It clearly changes. So that's what I was trying to point out. The tension in the strain will actually change when it's accelerating. Good? Okay, let's get to work on this problem up here on the board. Hang in. Break time's coming. Whoops. Break time's coming a little bit. Okay. What do I call this one? 5.28. Sorry, no half for you, right? There's a scale here. There's a pulley here. Pulley here. There's a scale here. There's a mass 1 here. There's a mass 2 here. And so this scale is reading tension 1. This scale is reading tension 2. And in this case, you agree this block we saw accelerated upwards. I'll call that A1. This block was accelerating downwards. I'll call that A2. Now, we generally have to pick a coordinate system. I'm going to choose the standard XY coordinate system for this one. Okay, just like in the picture. I want you to watch my hand for a second. I know you're tired. I know you're ready for that break. Tough it out. Watch this. This is the trick. I'm going to imagine, in this case, the Y coordinate is like my fingers here. The X is like my thumb. And I'm going to follow the strain. And it's going to flip. Do you see that? And that causes this to be the Y direction. Which way is X? Back this way? Whoops. All right. Now you may be saying, this seems silly, Rob. There's a couple of reasons for doing this. Number one, there's a trick that we'll be able to use later that will speed up your algebra. Number two, it actually foreshadows circular motion where the coordinate system spins around. Number three, I do this in the solutions all the time, so you got to get used to dealing with it. So there's the 3 reasons I want you to get used to dealing with this weird trick of letting the coordinate system follow the strain. Got it? You don't have to do it, but I think you should start doing it because of all those reasons I just discussed. Okay, standard practice. Okay, go. Figure out the FBD. Oh, wait. I don't want to go yet. There's 3 things I got to discuss. Part A. What does part A ask?
assuming that A1 equals A2.
Yeah, we assume A1 equals A2. Why? What words in the problem allow us to make this assumption? In particular, I'll read it out loud. We got an Atwood's machine. The pulleys are massless. They have negligible axial friction. The string is inextensible and massless. Mass 2 is larger than 1. The system is released from rest. The left scale reads T1. Okay, whatever. One of those words in particular helps us understand that this should be true. Inextensible, correct. Now, what does inextensible mean? Not stretchy. I'll get out of the way. We're saying the string isn't stretchy. So think about it. If the string isn't stretchy, don't the two objects have to move the same amount? So if one accelerates up this way, two would have to accelerate that way, the same amount, same magnitude. So that's what allows us, now careful. A1 is the magnitude. A1 with this arrow upwards is acceleration 1 vector. So to be clear, A1 does not equal A2. It equals negative A2 if you put the vectors on top. If you leave the vectors off, it's just the magnitudes. Everybody cool with that? All right, all right. What's that?
Would they still be the same though? Because the coordinate system gets flipped around.
Let's discuss that another time. Yeah. So what I want to do is just say I would say that's a tricky question, and I wasn't prepared to answer it. So how about that? Let's just focus on this. Do you agree with that statement? Yeah. I'm just gonna, I don't want to say the two acceleration vectors are the same. I guess what we would want to do is, do you agree technically I should say it like this, a different X and Y axis? So in this one, you could say A1, I guess I'm answering that. A1 vector is equal to A1 in the J hat, or it's equal to negative A1 in the J prime hat, whatever that would be. I don't even know how to draw it. You know what I'm saying? Is that what you needed, or should I shut up?
I think I'll understand it.
We can talk about it more after. It's subtle. That's a subtle thing, and it's going to take a little bit of effort, and it's not worth talking about. How about that?
Okay.
And I'll bring it up later if you care on the break. B. What's part B? We assume A is constant. We're assuming the acceleration is constant. What aspect of this problem allows us to know that the acceleration should be constant?
Release from rest.
Nope, not release from rest. Release from rest tells us the initial velocity is 0, but it doesn't tell us A is constant. That's a good guess, though. Somebody else. What were you guys thinking in the back? No. Good guess, though. Not the pulleys. So there's only, that's already there. String doesn't have mass. Think about it like this. Imagine if instead of a string, I used a giant heavy chain. As this one falls down, wouldn't you be shifting some of the mass from this side to that side? It would make the acceleration faster and faster. So it's the massless string. That's the key word. Now, let's be real here. Do you agree that all strings have mass? So it's right. So I guess you could say low mass. But a lot of times physicists are lazy and say, assume the string is massless. Then what they mean is, whoops, not low string. Low mass. Basically, it's massless relative to the blocks involved. Sort of like the cardboard was massless relative to us. All right, part C. T1 is equal to T2 if what assumption is true? What's that? Nope. Inextensible. Well, we probably need that as well, but yeah. So that I guess that relates to it. There's another more critical piece that I want to focus on.
The masses are equal.
No, it's the pulleys. Yeah, so here. So sometimes we'll say we have an ideal string and ideal pulleys, right? You might be saying, what if the pulleys did have significant mass? Chapter 10, we'll do it later. Okay, so I promise we'll come back to this one. And that's why I wanted to focus on the pulley aspect. But certainly, it also relies on an ideal string a little bit too. But basically, these assumptions we're always going to make. We're going to assume ideal string, low mass, no stretch. Okay, and the other aspect is going to be massless, low friction pulley. All right, that's our two main assumptions. All right, so far so good. I'm never really going to force you to talk about this that much, but I just wanted to let you know. I was talking with an engineering instructor this morning. He's sitting in on the class. And he's like, yep, we talk about this all the time in class. So if you're going to be a mechanical engineer or a civil engineer or something, these assumptions will come up. Hopefully the second time you see them, that's when you'll really remember it. But for now, unless otherwise specified, you can assume this stuff is true. So if we have a single string like this, same tension. So now what can we do out of all this? All these assumptions are for this simple fact. These have the same acceleration magnitude. These have the same tension magnitude. And we could show that when we run it again. We could look at the two scales and see if they have the same tension. Now we could do our free body diagrams. You ready? Let's do it. We're almost there. 5 minutes to break. I appreciate you being motivated to keep working here. I know it's hard. Late in the day, you're tired. Ain't tough. Good. Somebody tell me a force for object one. Tension up. Do I need to say T1? No, we talked about that. What's another force? M1G. I like that you said M1. Okay. It's accelerating upwards. What's the force equation? Everybody cool with that? All right. Give me a force on object two. Same tension up. What else? And 2G down. What's the force equation for this one? Careful. What is it? Speak up. You got it.
M2D minus. Negative
M2. Careful. We're using this coordinate system, right? Look at it. M2 is down, it's positive. T is up, it's negative. A is down, it's positive. Excellent. Nice. Got it? And this is the one people tend to screw up. For the reasons, right? We're so used to saying shit, down, that's positive, right? I mean, negative or whatever. Okay, whatever. Just watch out. What was the check? Do you remember a check I told you? Look, these two arrows pointing the same way. These two give the same sign. These two arrows pointing the same way. These two arrows get the same sign. Okay, next. Check out this fun trick. You could figure out the acceleration by solving for t and plugging it in. Look at this. I'm going to stack these equations and add them. When you do the rotated coordinate system, Take a look. I can stack these equations and add them. What force drops out? See, the internal force drops out. You see it? What do we get? M2 plus, wait, M2 minus M1G? So that's a cool trick. If you use this rotated coordinate system where you follow the strength, and this will work with 2 blocks, 3 blocks, 18,000 blocks, whatever. You can just stack them and all the internals drop out, so you don't need a system FPD. And what do we get for A? I'm going to factor out that G out front. How can we check this? What's one way to check an equation?
Units.
Units. Kilograms over kilograms, check. It's got meters per second squared, the kilograms drop out. What's another way to check it? Does it have the right sign? If we assume M2 is bigger than M1, the answer is what? Positive or negative? Positive. Is that correct? If M2 is bigger than M1, should this be a positive number downwards? What else could we check? This is a tricky way to check your answers. It's a good physics trick to learn. What's an extreme case? Let's get extreme. What's that? Okay, if the masses are equal, that's a unique case. What do we get for the acceleration if the masses are equal? A equals what? G. If the masses are equal, what do you get on top? 0. Isn't that what we saw? It doesn't accelerate if you balance it. Nice. Does that make sense? Let's do another way. What if M2 is much, much bigger than M1? What would that be like?
1 equals 0.
Okay, it's kind of like M1. You could set M1 to 0. I mean, physically, right? That'd be like taking a piano or a Buick on one side and a feather on the other. If you put a Buick on one, or a bowling ball on one side and a feather on the other, how quickly, right? If this was a bowling ball and this was a feather, approximately what rate would the bowling ball fall at? At the same standard gravitational rate. We expect to get the answer G. Well, let's look at it. Right? Do you agree if M1 is negligible? We get G. Do you agree that if M2 was negligible, we get negative G? It would accelerate the other way. So we've checked this in a huge number of ways. If I wanted to learn about the tension, how could I figure out the tension? Oh, you're tired. This is it, I swear. If you wanted to get the tension, how could we get the tension? What's that? Solve for T, plug this crap in, rearrange it a little bit. Got it? If you needed to get the tension, you could do this at home. You could take that, stick it in there, or maybe, I guess I'd probably stick it in this one. Doesn't that look slightly easier to work with? I'd stick it in there, move some stuff around and group it and do some algebra. Cool? Now let's take that break. You earned that. That was rough. Good job, everybody. Oof. Oh my goodness. Well, I guess I could show you on your way out that it does have the same tension. I'm going to do that real quick. Show you that they really do have the same tension. Sorry about that. Oh my gosh. No. Gosh, the table's in the way. How's that showing up? Yeah. So all we're trying to do now is show that right now they don't read the same tension, right? But when I release it, you see it snapping the same tension? They really did. I'll do it again, one more time. All right. Huh.
Recalibration there.
High quality tension there, sorry about that. In this case, all that matters is that they snap at the same tension. We can see what we're trying to do. Yeah, right? So dumb. All right.
Oh my goodness.
I want to look at a new problem. Page 96, 5.41. I'm going to sketch it here. 5.41. Got this horizontal track like this. It's going to be a string. Goes around a pulley and goes back to a block over here. And I think this block is 1. Is that right?
Yeah.
Yep. Okay, and then there's a pulley here. Maybe I'll draw this pulley a little bit more accurately, just so it makes sense. Typically with a pulley, there's an axle at the center. And there's like this little thing holding the axle in place, all right? So that dot is supposed to be the axle. Okay. Then connected to that, another pulley over here. I'll be a little bit lazier. Maybe I'll just draw it. There's a mass here. I'm going to call M2, I think. If it helps you get a feeling for this, I've got it set up right here. Then whose head is that? Nope, I think it's Peter's. Yep. But you might be in there too a little bit. No, you're good. Oh, yeah, you are in there. Sorry. I'll go that way. Whoops. Oh, yeah, you're right. Sorry, I'm mirrored. I'm mirrored and like remote control is also mirrored. So yeah, there we go. That's pretty good. Now it's kind of hard to see. So you know what they say, count on McDonald's to make it all work out. That's some old poster board from McDonald's that I'm going to use. We used to use McDonald's a lot. They would help us out when we were doing the Friday night science shows. And they hooked us up with all kinds of weird crap, like straws. And I'm like, I need some weird poster board. Okay, here. Does that help you see the string a little bit better?
Yeah.
All right. So apologies if it's not perfect. There we go. That's looking pretty good. All right. So now the idea here is string goes around this pulley and goes back to this cart. Now, if I move this, it's going to start going. Because the other end here runs over to this hanging mass right here. The idea is when I let go of this hanging mass, this would fall. Now, if I take the stopper out, it's going to fall down. Okay. Everybody got an image for this, what this contraption is? If you're a mechanical engineer, you should be getting excited. Okay, because we're starting to get towards something that looks like a machine that a mechanical engineer might use. Go up to the board here. All right, in this case, my first question is, let's suppose object 2 moves downwards distance h. So let's say I let go of it, I pull the stopper out, I release it from rest, this one falls down distance h. My question is, how far will object 1 move? Will it move the same amount? Will it move twice as much? Will it move half as much? Or will it move some other amount? Again, we're wondering how much object 1 will move. Any ideas? Anybody want to take a guess? It's okay to be completely wrong. Just guess and we'll learn. You think it'll move more? Why?
Because the string on the bottom side of the string attached to 1 will get shorter because it couldn't be pulled the other way because that mass is like way heavier, or it's like stuck.
It doesn't have to do with the weights.
It's like
You're on the right track. Let me just let's just think about this. What is attached to object 2? the pulley. So I could call this the right pulley and the left pulley. You agree the left pulley is attached? Yeah. Okay, so now in this case, how much will the pulley move?
H.
H. Right, so that means the new distance. This is me trying to draw that in its new position, all right? You agree it would move distance H. So if it has to move distance H, how much string do you have to add to the top side of the pulley? H. How much string do you have to move here on the bottom side as well? So how much does object 1 have to move? 2H. Whoops. Think about this. You have to pull, like, let's say this is 1 centimeter of string. I pull 1 centimeter down. I need to add 1 centimeter to the top and move this bottom 1 centimeter. That's 2 centimeters this block has to move. Could we test that? I need a human being. Come on. Somebody come up here. I don't care who. The sooner we do it, the sooner we get out of here. You ready, Mark?
You told me out. Dang it.
All right. And then let me move this way. Yeah, you do. There, that's good. All right. So now in this case, here we go. All you got to do, Mark, is come over here. And I want you to stand right here. Well, actually, you know, you can stand this side. Here we go. Sorry about that. Not bad. It's been a long day. Okay. What I want you to do is I want you to look at this right here. Do you agree it's at 30?
Yeah, approximately.
Actually, let me do it here. Pretty close to 30, right? Maybe 29?
29.
Okay, you hold that. So now what I'm going to do is I'm going to go to the other end. This one's at 19. So what I can do is I can literally move this one 20 centimeters. So I'm going to move it from here to 39. And you could tell me how much that one moves. So if this one moves 20 centimeters, how much did that one move?
About 10.
About 10. So again, we see the hanging mass moves half as much as this one. Or said another way, this one moves twice as much as that one. So far, so good? All right. Let's give him a round of applause there. That was it. That wasn't bad at all, right? Okay. So we see that this logic is valid. I want to talk to you about one special part of this. Okay. I want to draw an FBD for the pulley itself. We haven't done a lot of pulley work, so I'm trying to teach you everything I can about pulleys that I can think of that might be useful. So I'm just going to be lazy here and draw the pulley as a disc like this, okay? What is one thing touching the pulley? A string. Do you agree we have two different strings here? So maybe I could call this tension 2, and up here, maybe I could call this, how about tension 1? All right, so do you agree with tension 2 this way acting on the pulley? What is another force that acts on the pulley? What's that? 2T1. There's the other tension. Now, this is where I want to get into some subtleties here. The string is coming off the pulley twice. So we should actually account for that tension twice. That's the standard technique. Now, you might be saying, wait a minute, how does that work? This is, got to listen very, very carefully. Okay, and I'll even write it. It's very subtle. Friction is what makes this tension diagram accurate. Now wait, I thought you said these pulleys we were going to assume had no friction. Here's the trick. Pulley has negligible axial friction. Okay? friction between edge of pulley and string keeps string from slipping.
There's no friction, it would just slide over.
And the pulley wouldn't rotate. So think about it. If there was no friction, the string would just slide over the pulley and it wouldn't twist. But we know in reality this twists. What's crazy about this is it is this friction between the edge of the pulley and the string, which allows us to say, it's basically like two forces this way. Got that? It's crazy. So basically what I'm saying here is we're never going to say this stuff over and over again, sort of like the last problem where we wrote all those assumptions and we'll never use it over and over. I just wanted you to know that we could draw this FBD here like this. But wait, there's one more force acting on this pulley. What is it? But wait, yes, right? I'm going to draw a second version of this FBD. You agree there's the mass of the pulley times G downwards. Now think, if you put this weight on there, something would be wrong. The weight should be pulling the pulley down, but the pulley's not going down. That means the tensions are not actually perfectly horizontal. If you look at the string, whoops, oh geez. Zoom in as much as we can. That is max zoom. Look at that. Do you see how there's a slight angle on these strings? All right. So I just want to point this out. Technically, it should look slightly more like this. However, if the mass of the pulley is approximately 0 compared to the other forces involved, meaning if this weight is negligible compared to the tension, meaning if you use a heavy cart and a heavy hanging mass compared to the pulley, these pulleys are almost negligible. If that is the case, which is approximately true in this experiment, that allows us to draw these arrows perfectly left and right. Are you okay with that? All right. In this case, right, if this is not accelerating, do you agree we could say T2 is equal to 2T1? Or actually, let's do the force equation here, right? Right? I know you're tired, hang in there. This is X, this is Y. It's going to accelerate this way with some rate A2, right? If it's connected to block 2, it should have the same acceleration as block 2. In this case, I just wanted to point out, we get T2 minus 2T1 equals mass of the pulley times A2. But if mass of the pulley is approximately 0, this tension is twice as big as that tension. We see our first example of a force distance trade-off, right? We see that, look, this moves twice as much, you have half the tension here, right? Or said another way, right, you have twice as much force over half the distance to make this thing move. Okay, that's fine. Questions on that? You could draw FBDs for pulleys. Let me ask you this. Will these two blocks have the same acceleration? Will acceleration of 2 be the same as acceleration of 1? What do you think? How do they relate? Exactly. Think about it. If this one has half the distance, it should have half the acceleration. Agreed? Or you could say this, y, you could take two derivatives of it and you get the acceleration. Or you take two derivatives of this, you get the acceleration with a factor of 2. So notice A1 is equal to twice A2 because it's moving twice as far. So at this point, you could do all this crap. All right. What do you think? Feeling good on that? It's kind of an advanced, I don't know, mechanical engineering type of trick. All right. I got another one for you. And after this problem, I'll tell you some good news. Okay. All right, we're going to this green screen, so I think it's you guys. Yep, you two. Sorry. Jeez. It's always somebody moving, right? Sorry about that. And I'm gonna have to move that table in just a second. Okay. Now I need to move this table here. Thank you guys for always moving around. Appreciate it. You see the maps at the bottom or not? Yeah.
No.
Okay. Got it? Okay. We're looking at a device here. This is kind of complicated looking. I want you to look at this thing. Notice what we've got here. We've got a pulley right here. We've got a pulley right here. We've got some scales. These big rectangles are scales or square things, all right? And I can lift this object up, right? This object, or this contraption, I should say, has a name. Does anybody know the name of this weird contraption? This is called a block and tackle. Have you ever heard that before? If not, this is a block and tackle. Now look at this thing. What I could do, I could turn all these scales on. What we could do is I could see how all these scales read, right? And so what we'll do here is actually, let's make a picture of this on the board real quick and then we'll come back here. Actually, no, let's do the numbers. That way I don't have to keep walking back. So, all right, because it takes forever to get the camera set up, right? So what I need to do is I need to turn these scales on without any tension in the cable. That way they're zero. And now I need to pull very slowly so that the acceleration is negligible. LB. Okay, somebody write this track. Oh, wait. Okay, I gotta do it again. I think there was too much friction over here, so I'm gonna try this again. Ready? Okay. We got 2.8, 2.25, 5, 8.3. Did somebody write those down? 2.8, 2.25, 5, and 8.3. One last time. 2.8, 2.25, 5.05, and 8.3. Got it?
Got it.
Thanks. All right. So I'm just trying, I know it's maybe hard for you to see those, so I want to draw a picture on this board here, right here. What we see is 8.30, and actually those were, okay, whatever. I'm just going to say these are newtons, all right? The scales are actually reading slightly different units. And then there was a pulley here. There's a scale here. What was that, 2.25?
Yes.
And I think these are like hexagons, but whatever. What were the other numbers?
5.0 and 2.8.
Okay, thank you. Now this is not perfect. This is the real world, right? So I'll try and explain this and see what we get. So these scales are reading the tension. This is where my hand was, right? So this, and I'll try and make the pulleys look a little bit distinct. So these will be the pulleys, these circular looking things here. All right. In this case, I want you to try and imagine the FBD for the upper pulley here. So let's look at that. Here's the upper pulley. In theory, what are we seeing here? If it helps, let me outline this rope in red. This rope going all the way around here, all the way around here, all the way up here to the center of that pulley, right? It's connected on to the center of that pulley. Now notice, this scale was reading 2.8. This scale was reading 2.5. What's the average of that approximately? About 2.5. So yes, when I'm pulling this thing, the problem is when you're actually moving something, there's a little bit of acceleration, and sometimes these things lock in on a different number. So I'm going to take the average of these two readings conveniently as 2.5. Okay, so that means on average, we could say I was pulling with 2.5 here and 2.5 here. Right? Let's look at the forces on the upper pulley. How many 2.5s are acting on the upper pulley? How many? Three. Three. You see it? 1, 2, 3. Okay. So we have 3 of these 2.5 newtons. That's approximately 7.5 newtons. What is the upwards force? About 8.3. In practice, if these were real numbers, this pulley would accelerate upwards, right? If you had more tension upwards than the net force downwards, it would accelerate upwards. We know that doesn't happen though. So what we're seeing here is there's some slop in these scales of about a newton. But we do see that these forces are approximately balanced as we expect. Okay, now let's look down here at this lower pulley. Right, on the lower pulley, what are the forces upwards on the lower pulley? 2.5s, excellent. See what I was saying? Oh, how convenient that I'm going to average it to 2.5. What's the force downwards on this pulley? 5 newtons. So it's looking pretty good. And again, we know there's some problems with the scale readings. We saw it floating around by at least a half a newton, right? Somewhere in that half a newton to 1 newton range. But notice the forces do seem to make sense. What is the frickin' point? I was able to lift something that weighs 5 newtons by pulling how hard? 2.5. I was able to lift an object with half of its weight. That's cool. That's the point of a block and tackle. It doesn't come for free though, right? If I just pulled up on this, or if I just used a single pulley, right? 5 newtons would be what I have to pull, right? And then actually there'd be a different force on the ceiling too, right? So the forces on the ceiling get affected by this weird contraption. There's a trade-off though, right? I'm able to use half the force. So how much rope do you think I need to pull? Twice as much. Let's do a quick check. We can look at this thing. If I pull 1 meter of rope, how much should this block go upwards? I'm getting a force doubling, so what has to happen? If I get twice as much force, what happens to the distance? Cuts in half. We're going to learn an equation later called work. And it's going to relate to force times distance. And more on that in chapter 7. Buy your volume 2 now. Okay, yeah. But look at this. The idea is if you use twice as much force, you need it's going to move half the distance. Or if you use half the force, you need twice as much distance so that you can do the same amount of work to lift something. Yes, question?
This could change how many pulleys
Yes, you could use a block and tackle, like, so what if you did a whole bunch of these pulleys, right? You could get this to be very advantageous. So if you're trying to pull an engine block out of a car, you could have like 4 pulleys on top, 4 pulleys on bottom, and you get a multiplier of 8. But that means to move the engine block 1 foot, you'd have to pull 8 feet of chain. Got it? And that's the cool days. Anyways, let's do a quick check on this, see if I'm lying, and then I'll tell you the good news, okay? Oops, wrong way. You'd think I'd get used to it, but I don't. I just have too many remotes. All right, so here we go. I got 2 meter sticks here. You want to help me out real quick? Sure. Okay. You agree that this is basically a 50 centimeter meter stick? Oh, wait, there's the phone. So now what I'm going to do is I'm going to try, I want you to basically hold that right there like this. And so the idea is look at the bottom of this weight. I'm going to lift this up. So I'll pull this one down. I'll just go to the, I guess I got to go basically about to right there. Got it. Right. So I'm going to think, I want to pull this basically down to where the top of the weight is. This will be 1 meter, right? See, it's approximately 50 centimeters. So again, we get this force distance trade-off. Got that? All right, let's give a round of applause. Oh my goodness. What's that margarita? You want the good news now? The stuff on pages 96 and 97 are not on the test. But if I told you that at the beginning, you wouldn't have listened, right? Now, to be fair, I do think it's important that you learn about how to draw a free body diagram for a pulley, right? But this stuff where there's this is the subject of mechanical engineering. If you're passionate about that, you should check that out. Got it? Everybody understand? I'm not going to put one of these on test. What? What test? Yeah, whatever. Test 2. Remember, chapter 5 is on test 2. All right. Good. It's pretty cool stuff. So if you want to see how multiple pulleys would affect that, we could do that later. An example of one of those is actually at the bottom of page 97 with Chewy and Zool. I don't know why, but I thought it'd be cool to have 2 names in the problem that had UE in it. So Chewy and Zool. What's that? Well, Zool was like a character from the original Ghostbusters, like the evil demon Zool or something. I don't know. And then Chewy, I guess that's just a nickname, right? Is that a nickname for Jesus? Something? I don't know. Somebody told me what that nickname was, and now I've forgotten. I don't remember anything. My brain's gone after COVID. But yeah, I when I was in Taiwan, I went to a children's science museum, and they had this exact setup, and you could pull this up and do that. So I don't know. It was pretty fun. I always dreamed about doing that and making a student do that. You guys want a fun question for just kicks? Sure. I have a puzzle for you. How about this? Let's do. I'm curious if you think this is possible or not. Okay. We're done with this one. It was educational. It's useful stuff. We will talk more about force distance trade-offs later. Like I said in chapter 7. Physics gets interesting if you just give it some time, right? You got to work at it. Test 1 is like the most boring stuff ever. So you got to do it. You got to be good at it so that you can do something you care about later. Here's a question. I thought about getting some student that's just jacked out of their mind and could really lift a lot of weight. Thought about taking this. Take the railing outside, run a cable down here, and then I have basically a large platform they could stand on. And on this large platform, you could have a pulley this, bolted onto it, the string, oops, oh, whatever, we'll put this platform over here, right? And then imagine you have a super jacked up student standing here My question is, could a student standing on such a contraption lift themselves up in the air? Take a second, debate. Think about it. We've been talking about all this Newton's third law all day. We've talked about pulleys. It's kind of a fun one. In theory, could a person standing on this contraption lift themselves, or is it impossible? Take a second, debate.
I think unless if you can bring down something.
You could depend on how much you see the cameras. And only, but also depends on how much the
The police, doesn't have the weight, so he's trying to trick us, so much the opposite. Let's say no.
The person's gonna try and pull the rope upwards, right? If the person lifts the rope over their head, what I'm wondering is, will they go off the ground or not? Or is it impossible? That was the problem. We killed off somebody's Zoom session. Right? That's what I love about that thing. So this is what it's like as a teacher. You hear that beat, you're like, okay, there's somebody else that just couldn't take it anymore. Which I can understand. We've all been on that Zoom meeting where you're just like, screw this, I'm out of here. If you wanted to find out if this was physically possible, what's something you could do to analyze this situation? Draw an FBD. Now, I'm going to draw a system FBD of the human being with the thingy, right? There's the person. Let's just say the person is a block. Okay, that's the person pulling on the rope. Okay, there's the person. Now, in this case, there's a tension going up, right? What about on the human being? Which way is the rope acting on the human? Which way does the person pull on the rope? So which way does the rope pull on the person? Down. Let me make these the same size if it's easier. Is that it? Is there another force on the pulley? The rope pulls up on the pulley twice and down on the person once. Does this look vaguely familiar? That stupid fan cart with the U thingy tubey, whatever. Oh, that's a YouTube. Oh man, I invented YouTube. Whatever. Okay, in this case, what is the sum of forces in the y direction? Isn't it just T? What is the mass I need to use here? Oh wait, there's something else acting on it. I forgot. What else did I forget? Weight, right? You mean there's M total G? Well, let me rewrite. Sorry. There has to be the weight there, right? I forgot that. That was dumb. Now look at this. You agree the tension, in order for this thing to go upwards, has to be mg plus m ay. What if you lift this at constant speed? If you lift it at constant speed, what's ay? 0. What is the mass involved? It's the mass of the human plus the mass of the platform. Is it possible for someone to push more than their own body weight? Has this ever occurred in the universe? In the Olympics, maybe? You put some squats on there and you can do it. I can't because I did lunges yesterday morning and I just about killed myself. I'm about to fall over up here. But it is possible, right? If you were yoked, you could totally do this. Now, keep in mind, how far do you think you would be able to pull this rope exerting a force greater than your weight? I could imagine if you had a squat, right, and you had a bar that you put on like shoulder harness, you could move yourself like a foot upwards or something, right? But then think how unstable this would be and dangerous, and someone would get hurt really bad. We should totally do it, but I haven't gotten around to it. It's on my list. Wouldn't that be fun to try? And just see people try to, like, imagine you start, as soon as you start lifting off the ground, you'd be like, whoa, and you'd fall over and totally get a bloody nose or something. Something to do next year. Crazy, right? Isn't that weird? At first, you're like, wait a minute, what forces did I not talk about? Internal forces, right? By drawing a system FBD, we didn't have to think about the internals. You might be saying, well, wait, the person exerts a normal force down on the sled, but the sled exerts a normal force up. Oh. By doing a system FBD, we don't have to think about that. You want a fun variation? Sure. Because I'm going to give it to you regardless. Look at problem 5.33. 5.33. Okay. All right. For reference, 5.33 looks a little bit different. Right, and there's somebody sitting here, organism A. We've got a really long arm for some reason. Vampire-like claw at the end. Yes, question.
What's that thing called again?
Block and tackle.
Block and tackle.
Yeah, block and tackle is actually it's on page 97.
So could you use that to pull yourself up and then it would, oh, that's what this is?
This is called a bosun's chair. So it's actually very similar. BOSUN''S. So now look at this one. Here's the system FBD, right? There is the system. What is one force that acts on this system? Give me one force, somebody. mg, right? And I'll call that m total g, the mass of the chair and the girl sitting on it. What else? What's another force acting on it? How many times does the tension touch the system? Yeah, 2. Tension. So in this case, this is a much smarter way to do it than that last one. This is about the dumbest way you could ever think of lifting yourself. You'd be better off just pulling on the rope so you don't have to lift the platform, right? Think about it. You can just climb the rope. It's a lot easier. You don't have to lift the damn platform. But in this case, why is this better? In this case, you have 2t minus mg equals m total A. And so in this case, you could easily imagine yourself causing yourself to accelerate upwards, right? Because you could just keep pulling rope. And so this would be a lot easier because you're getting, right, the tension, you get to double it. So you get this force distance trade-off. So far, so good? Yeah, I don't know. Yeah, so we can see that there's different designs you might use. Oh my gosh, I'm tired. You guys got gas in the tank for one last one or not? Sure. Do any one you want. I recommend 5.32. Yeah. Let's just try and get the FBDs done. And on problem 5.32, it's at the top of page 93 in my book, 5.32. Remember that trick I was telling you about the hand? Like try to use the rotated coordinate system, right? Just follow the coordinates around all those different pulleys and just get the FBDs drawn in the coordinate system. Don't worry about anything else and then get the hell out of here. Okay, 5:32, I'll catch up. Talk as much as you want or run out of the room if you want. If you're just tired and want to quit, that's fine, I understand. I'm gonna do it. I appreciate that you guys are troopers and that you're just hanging tough. That's awesome.
Yeah, I never thought about it until now. Wait a second, that reminds me of something. Did machines. Sounds like you've received like extension. Pulley first. It's like every machine I do.
Masses and angles are all, oh, this is angle theta. Kind of a good summary of everything that we've done. Is friction negligible? Yes, friction's negligible, good. And we're told the rightmost mass is going to travel to the right. So, okay, starts from rest. So do you agree this one's going to accelerate this way? I think that's what the problem is telling us. I'm going to choose this coordinate system like this. I know you're maybe tired, but maybe you could just give me a heads up here. I want to show you something. Watch what I mean, right? Just follow the string. Again, I follow the string. And I let this be my axis. Why? When I do this, do you agree all of them are accelerating in the x direction? Even this crappy one? Right? If we call the x direction the direction the string moves and rotate our coordinates accordingly, that should work out. You want me to keep writing up here while you work, or what would you like me to do? You want me to just write up the answers real quick or not? Let's do it real quick. Forces on one. I'm going to call it tension 1, M1G. That's it. On block 2, what's one force on block 2?
M2G.
M2G. What's another one?
Tension.
Tension. Which way? The left? Which tension is that going to be? The same as this one or a different one? Same. So let's call that T1. What's pulling this way then? Same string or different string? Let's call it T2 because it's a different string. What's keeping it from falling down into the molten lava of the earth?
Normal.
What would I call that? Normal 1, 2, 3, 4, 5, 7, 8 times pi?
2.
Yep. Now let's get over here to 3. What's one force? mg. Which way? Only straight down. Don't overthink it. Okay. What's another force? What's this one called? C2. What's this one called? Call it T3, sure. Anything else? Which way? Show me with your fingers. Which way is the normal force? Yes. Perpendicular, normal to the surface. Got it. And I'm going to call that normal 3. Check me right here. Tell me what I do right or wrong. Tell me if this is correct. Am I splitting up the components correctly? No, these don't match those. Bad. Does that match those? What's this angle? Theta. mg sine or mg cos? Opposite. m3g sine. This side. m3g cos. Over here to number 4. What's one force? mg. 4g. Good. What else?
T3.
T3, right? This row is T3. So the pulleys redirect the tension. What's the normal force? 4. And then there's this force over this way. Is normal force 4 equal to M4G? Why is normal force 4 not equal to M4G? These two equal M4G. Do you see it? This one plus this component add up to M4. You see what I'm saying? Sometimes normal force is not mg. Sometimes it's not mg cos. Sometimes it's whatever it is. F sine or cos? Sine. Cos. Now, check this out. Watch this. This one's accelerating this way with A, right? This one's accelerating this way with A. This one's accelerating this way with A. This one's accelerating this way with A. Agreed? Look at the force equations. I know we're over. Well, we're only 1 minute over. We're going to be done. Give me the force equation right now for this one.
T minus M1G.
Somebody else, give me the force equation in the x direction for this one.
T10 minus T1.
T2 minus T1 equals M2A. Good. All right. Somebody left the hard one. Okay, somebody else, give me the force equation for this one.
T3 plus M3G sine of theta.
Running out of room. Minus T2. Anything else horizontal? No. Equals? Which end?
M3.
Last one? Somebody else. You got it. Finish strong. Forces in the X. F cos. Sorry, I was unclear there. My bad. Minus T3 equals. If you want to find the acceleration really quick, how would you do it? Stack them and add them. When you add them, which forces will drop out? The tensions are all internal. Do you agree?
Yeah.
You guys did pretty well on that. And I don't like to compliment people. Nice job. Way to finish strong today. What do you think? You could do this, right? Yeah. You just got to work hard on test 1, and then this test will be, well, hard 2, but yeah. Hard in a different way, right? So far, you're doing really well at this stuff. So hang in there, study your ass off for test 1, all right?